Maths for Construction, Introduction to Beams, and part one of this video is some pretty basic stuff about forces and beams. So this is a beam. Buildings are made out of beams, lots of beams. You need to know how to calculate the forces that act on beams, and you also need to know about turning forces or moments. Okay, we only need on our course to know about simply supported beams. And a simply supported beam will have a pin joint, like a hinge at one end, and then a roller joint at the other end. Don't worry too much about that. The point is that for this type of beam, we only need to worry about the vertical forces acting on the beam. Talk about forces for a bit. Force is measured in newtons, capital N, or kilonewtons. 1,000 newtons is a kilonewton. Think of a force as a push or a pull. Mass is measured in kilograms. Mass is how much of something that there is, and a mass of 1 kilogram has a weight of about 10 newtons, a little bit less than 10 newtons. So 1 kilogram has a weight of 10 newtons, 9.8 actually. Now, if an object is not moving, then it must be in equilibrium. Now, what does equilibrium mean? That means that all the forces acting on it cancel. There's no resultant force acting on it. All of the forces acting on it cancel. And that's useful. That means all the forces up equal all the forces down. Consider this. This cup isn't moving, so we know that this cup is in equilibrium. So all the forces acting on it must cancel out. What forces are acting on it? Well, there are two forces acting on it. There is the weight of the cup downwards, and there's something that we call the reaction force, which is the push of the table upwards. We call it the reaction force because if the weight wasn't there, then it wouldn't be there. It's reacting to the weight. Now, because the cup is in equilibrium, we know that these two forces are equal and opposite. We know that R equals W. So if we know the mass of the cup, we work out its weight, multiplying the mass by 10. And then if we know the weight of the cup, then we know what the reaction force is, because it's in equilibrium. Now, this beam is in equilibrium as well. So vertically, all the forces acting on it must be equal and opposite. We have the weight downwards, and the two reaction forces are at the ends, at the supports. So W equals R1 plus R2. I'll notice on our course they call it RL and RR, left and right. But I'm going to call it R1 and R2. And in this particular case, as the 10 kilonewtons is in the middle, then these two forces will be the same. There'll be 5 kilonewtons each, because 10 equals 5 plus 5. You'll probably get a question where you have to work out what the reaction forces are, and that's something that we'll be learning to do in these videos. Here are some questions for you to do. Okay, what's the only type of beam we need to know about? It's simply supported. What's the weight of a 1 kilogram mass? It's about 10 newtons. What would the weight of an 80 kilogram person be? Well, that would be 800 newtons. How would we know if an object is in equilibrium? By looking at it. Well, it's not moving. What can we say about the forces acting on a beam in equilibrium? Well, all the forces up equal all the forces down. All the forces acting on it cancel. What do we call the forces that act on a beam at its supports? They're called the reaction forces. And the beam supports a single point load of 60 kilonewtons at its centre. So R1 and R2 will be 30 kilonewtons each. 30 plus 30 equals 60. Moments. Maths for Construction, Introduction to Beams, Part 2 is about moments. Look at this beam. Now, the two reaction forces aren't going to be the same. One of them is going to be bigger. Which one is going to be bigger? Well, to me it's pretty obvious that R2 is going to be bigger. Imagine these two fellas here carrying this plank. Now, which one's got an easier job? And I reckon R1's got an easier job. You know, the guy B has definitely got the heavy end. So R2 will be bigger than R1. R1. How do we actually work out R1 and R2? Well, we're going to use moments. Now, what are moments? A moment is a turning force. A turning force, a torque, T-O-R-Q-U-E is another name for it. A turning force, a torque, a moment. Moments act about a point called the pivot. That's the turning point, is the pivot. A moment might be clockwise or anti-clockwise. If you look at this diagram of a spanner, you can see where the pivot is. That would be where the nut is. And then this force is producing an anti-clockwise moment about the pivot. It's trying to turn the whole thing anti-clockwise. Now, to calculate the size of a moment, basically moment equals force times distance. Force times perpendicular distance, actually. So in this example, 300 newtons times 0.2 meters will give us a moment of 60 Newton meters. Moments are measured in Newton meters or kilonewton meters if it's a big force. Moment equals force times distance. Now, we said earlier that if an object is in equilibrium, then all the forces on it must balance. Something else, all the moments have to balance about any point. Usually we choose a point which we call the pivot, and all of the moments about that point must be the same. The clockwise moments must equal the anti-clockwise moments about any point. Looking at this diagram, the weight of the girl is going to produce a clockwise moment. It's going to try and turn the seesaw clockwise. The weight of the boy is producing an anti-clockwise moment. His weight is trying to turn the seesaw anti-clockwise. And as the seesaw is balanced, the two moments must be equal and opposite. Okay, there's the clockwise moment and the anti-clockwise moment, and they must balance, the equal and opposite. Let's put some numbers on that. Because the beam is in equilibrium, the moments about the pivot must add up to 0. So the anti-clockwise moment equals the clockwise moment. Now, if the boy has a weight of 800 newtons and he's 1 meter away from the pivot, then the anti-clockwise moment will be 800 newton meters. The girl has a weight of 400 newtons. She's 2 meters from the pivot. So the moment due to her weight is a clockwise moment of 800 newton meters. So the two moments cancel. It's in equilibrium. It's balanced. Here's a couple of questions for you to have a go at. Pause the video and have a go at them. Maths for Construction, Introduction to Beams, Part 3 is about reaction forces. We've talked a little bit about reaction forces anyway. What we're going to do is we're going to figure out how we can work them out. Let's look at this example again. So we've got R1 and R2 are the reactions at the supports. Now we know that R1 plus R2 equals 60 kilonewtons, but we don't know what R1 and R2 are. What we can do is we can use moments to find out. And what we're going to do is we're going to take moments about one of the supports, and usually the one on the left, point A, is where the beam touches that support, and we're going to take moments about point A. Why do we take moments about that point? Because basically then we don't have to worry about R1. R1 won't come into our equation because the force R1 actually goes through that point. It's not going to have a moment. The distance is 0, if you like. There won't be a moment. So we don't have to worry about R1. So we're going to take moments about point A. So the anti-clockwise moment equals the clockwise moment. Looking at the diagram, you should see that this force R2 is going to produce the anti-clockwise moment, which will be R2 times 10. And then the clockwise moment about point A is 60 kilonewtons times 7. So R2 times 10 equals 60 kilonewtons times 7. So R2 is 42 kilonewtons. Now that we know what R2 is, a very simple way to find R1 Well, remember that R1 plus R2 was 60, so R1 must be 18 kilonewtons, 60 minus 42. We could also take moments about B to find R1, but this way's a little bit simpler. Okay, here's one for you to do, kind of fill in the gaps. Okay, what you do to find R1 and R2, take moments about point A, the left end of the beam. There's an anti-clockwise moment due to R2, and that will be R2 times. And then there'll be a clockwise moment due to the 200 kilonewtons, and that will be, and blah, blah, work it out. Very important, there are two types of load. There is a point load. All of the loads so far have been point loads, and there's also something called a uniformly distributed load, or a UDL. Imagine we had 200 kilograms of sandbags and we spread them out over a beam of length 5 meters. Now, 200 kilograms has a weight of 2,000 newtons, so 2,000 newtons over 5 meters is a UDL of 400 newtons per meter. Okay, it's a uniformly distributed load. It's not acting at a point, it's acting over a length of beam. There's two symbols we can use for a UDL. In the Maths for Construction exam, it'll probably be the one at the top, the one with these circles on it. Although most websites and things, you'll see the one below it. They're just two different ways of representing a UDL. Okay. If there is a question with a UDL, then what you'll probably have to do is work out the equivalent point load. If you had a UDL of 20 kilonewtons per meter on a beam of length 4 meters, then that is the same as, it's equivalent to a point load of 80 kilonewtons in the middle. Yeah, 20 kilonewtons per meter for 4 meters. 20 kilonewtons times 4 is 80 kilonewtons. And that will be acting from the middle of the beam in this case. Here's some that you can have a go at, pretty straightforward. What would be the equivalent point load for each of these UDLs? Maths for Construction, Introduction to Beams, Part 4, Calculating Reaction Forces. I've already shown you how to do this. This is a bit of practice calculating reaction forces. Okay? Let's say we have to calculate R1 and R2. I'll do a couple with you and then I'll leave you one to do by yourself. So what we're going to do is we're going to take moments about, we're going to take moments, before that actually, what we can say is that R1 plus R2 equals 150 kilonewtons. We'll use that later. And then we're going to take moments about A, and we say that the anti-clockwise equals the clockwise. Now, the anti-clockwise moment is R2 times 11 meters, and there are two clockwise moments this time. There's 50 kilonewtons times 4, and there's 100 kilonewtons times 8. So we're going to end up with an equation which is R2 is 1,000 divided by 11, which is 90.9 kilonewtons, and then when we know R2 we can work out R1 because we know what R1 plus R2 equals. Here's another example, but this one has a UDL. Okay, so to work out R1 and R2, again we're going to take moments. Actually, before we do that, what we have to do is change the UDL to a single point force, to an equivalent point force. If you could do the examples a little while ago, you should know that this particular UDL is going to be the same as a 40 kilonewton force 2 meters from the end of the beam, 2 meters from A. Now that we know that, we can say that looking at the vertical forces, we know that R1 plus R2 equals 40 kilonewtons. Okay, we're ready now to take moments about A. If we take moments about A, we can find R2. So anti-clockwise equals clockwise. So R2 times 7 equals 40 times 2, So we've got R2, 11.4 kilonewtons, and then we can quickly find R1 is 40 minus that is 28.6 kilonewtons. Okay, you do this one all by yourself. Maths for Construction, Introduction to Beams, Part 4, Shear Forces, Shear Force. It's getting a little bit tricky now. We've moved away from the basics. It's not easy now. It's getting a little bit more complicated. Shear force. Okay? Now, there are external forces acting on the beam and there are internal forces. External forces are from the outside. The loads that we put on it, the reaction forces. But inside the beam, there's an awful lot going on. There are internal forces and moments, and it is those that will cause the beam to fail. If we looked at a slice of our beam, if we looked at what's happening inside the beam, we'd see that there was something called shear force and a bending moment on any particular cross section. And this is very important. What are shear forces? Well, they are inside the beam. If you imagine looking inside this beam, one end of the beam is being pulled downwards, the other end of the beam is being pushed upwards. It's in equilibrium, but there's like a slicing, cutting action going on inside the beam. That's the shear force. And when the load on the beam is too big, it is these shear forces which will cause the beam to fail, to break. Now, how do you work out the shear force? It's very simple. The shear force at any point is equal to the sum of the vertical external forces acting left of that point. If we pick a point X, well, a distance X from the left end, then just look at the forces acting on the beam and figure out what's the resultant force left of that point. Okay, consider a point a distance X from the left end of the beam. Now, looking at this diagram here, there's only one vertical force left of that point, and that is 50 kilonewtons upwards. So the shear force at that point is 50 kilonewtons upwards. If we look further on past the midpoint, now left of this point, there are two forces acting on the beam, two external forces. There's the 50 kilonewtons upwards, but there's 100 kilonewtons downwards. So the shear force at that point is 50 kilonewtons downwards. Okay, if we did a graph of how the shear force varies with distance, what would it look like? And the answer is it would look like that. And this is called a shear force diagram. It's how the shear force varies along the length of the beam. This is a very, very simple one. Usually they're a bit more complicated. If there's more than one load, or if there's a UDL, it gets a bit more complicated. In fact, that's what we're going to look at now. Things are a bit trickier for a UDL. Now, draw a shear force diagram for this beam. You might be told what the reaction forces are. You might have to work them out. In this particular case, it's pretty straightforward. We know that this UDL, 8 times 3 is 24 kilonewtons, so I know that the two reaction forces are 12 kilonewtons each. Again, let's pick a point somewhere on the left side of the beam, the left endish of the beam. Okay, consider this point here, which is 2 meters from the end of the beam. Now, what vertical forces are acting left of that point X? Well, there's the 12 kilonewtons upwards, the reaction force, and we're also at that point, left of that point, there will be a 6 kilonewton force downwards due to that part of the UDL. So the shear force at that point X is going to be 12 minus 6 kilonewtons, which is 6 kilonewtons upwards. Hopefully you can see that if X gets bigger, then the force due to the UDL will get bigger, so the shear force will get smaller. And then after the middle of the beam, the shear force will become negative. Okay? The shear force diagram for this beam looks like this. Remember that shape. Notice the shear forces are maximum at the ends. Shear forces are usually maximum at the ends. It gets smaller, it's zero in the middle, and then it gets bigger again in a negative way. Remember that shape. That's for a UDL, a single UDL. That's what the shear force diagram looks like. Maths for Construction, Part 5. This is about bending moments. Now, external forces produce internal forces and moments. And it is those which will cause the beam to fail. And engineers must know what these forces and moments will be when they design their beams. They need to know where it will bend most. They need to know where the internal stresses will be bigger so that they can reinforce the beam somehow to stop it from failing. And now we're talking about bending moments. Okay? So, as well as the internal shear forces, there's going to be internal moments. There's going to be turning forces inside the beam, and these are called bending moments. Now, to work out the bending moment at a particular point, x, let's say, a distance from the left end, then basically it's equal to the moments, the external moments acting left of that point. In this particular example here, if you look at the point, the external moment is 50 kilonewtons times this distance x. As we move away from the left end, this bending moment will get bigger and bigger. Okay? After the middle of the beam, what will happen is that the bending moment will get smaller again. Why? Because now there's the clockwise moment due to the 50 kilonewtons, but now we also have an anti-clockwise moment due to the 100 kilonewtons. So the resultant moment will be getting smaller. The 100 kilonewtons is producing an anti-clockwise moment. The resultant bending moment will now be getting smaller as x gets bigger. When we get to the end of the beam, the bending moment will be zero. Okay? And this is a bending moment for this particular diagram. In all of the examples that you get, by the way, on this course, for a simply supported beam, the bending moments are zero at the ends. At the ends of the beam, the bending moments are zero, and they're usually biggest somewhere around the middle. If there's just one point load in the middle, then the bending moment is biggest in the middle of the beam. Remember that the bending moment at any point, a distance x from the left end, is equal to the moment due to the reaction force minus the moments due to any external forces left of that point. Bending moments, well, they're moments, so they're measured in Newton meters or kilonewton meters. Now, if you didn't understand this PowerPoint, if there's anything you don't understand, go through it again carefully. There's actually lots of YouTube clips and articles on the internet that explain this stuff. Have a good look at them. You should have a student book. It explains it. I think it doesn't spend very long explaining it, which is why I've done this video. This example here where you've just got one external force in the middle, remember this shear force diagram and this bending moment diagram. Okay? Things get a bit more complicated if there's more than one point load, and if there's a UDL as well, it gets a bit more complicated. Do a Google search for something called a beam calculator, and there are programs that will actually work out the diagrams for you. You can't use them in the exam, but if you have a play with it, it'll give you a good feel of what the diagram should look like, what to expect. This is an example from the student book. I don't think you'll get anything harder than this. And this is the shear force diagram and the bending moment diagram for this example. And I worked that out using one of these tools on the internet. Last point about shear forces. Shear forces try to cut the beam, try to slice it in the middle. Shear forces are usually biggest near the ends of the beam, as I told you earlier. So the beam needs to be stiffest near the ends. Make your beam stiffest at the supports, because that's where the shear force is going to be biggest. A simply supported beam is going to bend the most in the middle due to the loads acting on it. The top of the beam will be in compression. It will be squished together as it bends, and the bottom of the beam will be in tension. That will be stretched as it bends. Bending moments are usually biggest around the middle of the beam. That's where the beam is going to bend the most. Depending on where the loads are, it'll be around the middle of the beam. The biggest bending moment, the greatest, is when the shear force equals 0. In this example here, it's exactly in the middle of the beam. So if you're going to stop your beam from bending, then that's where you need to reinforce it to stop it from bending. Some form of bracing, external bracing could do this, or you could make your beam a bit deeper, a bit more resistant to bending in the middle. Okay. Here's an example from the student book. Whereabouts should the beam be stiffest to prevent it being cut due to shear forces? And if you were listening earlier, you should know that that is at the ends of the beam. In fact, looking at the shear force diagram, that left end of the beam, that's where the shear force is greatest. Where would be the best place to add a side brace to prevent the beam from sagging? And in this particular case, looking at the diagrams, it's not going to be in the middle of the beam. It's going to be at about 2.8 meters from the left end. Okay, because that's where the shear force is 0. That's where the bending moment is a maximum.